Okay, so I'm going to talk about package management for HPC, but I wanted to give a little motivation in advance. I'm Todd Gamblin. I'm from Livermore. This is a project that arose out of real problems that we had fighting with HPC systems. So I think people are pretty familiar with the scientific software stack, but I wanted to go over a few packages. So this is Nalu. This is a package from Sandia. It's a generalized, unstructured, massively parallel, low Mach flow package. And Nalu is the little thing on the left-hand side there. And all the other pieces of this graph are things that Nalu depends on. So that's a pretty complicated package. That's quite a few different pieces. This is DL2. This is a C++ finite element library. DL2 is, again, the thing over on the left there. And then there's the Trilinos cluster in the middle. And then there's a whole bunch of other dependencies in there. Some of them you're probably familiar with, MPI, other things. And then if you go out to some of the data science libraries that people are using, there's even more complicated packages. So this is RMiner, which is a data mining library. The left-hand side of that is all the stuff that is in R, and the right-hand side of that is all the stuff that's not in R. And so, yeah, things get pretty nasty. Even for proprietary codes, they're based on many open source libraries. And this is one of our Livermore codes. It's an ICF code that we run. All the blue stuff in this diagram is open source. And so basically half of this code is open source packages that are external. We don't control them, but we rely on them. And the other stuff is internal packages that we have to connect and make sure integrate well together at Livermore. And then if you go out to the scale of the US Exascale project, which I work on, there's a lot more packages. So there's 15 plus applications, and so you could imagine that each of those is like one of the diagrams I just showed. There's 80 plus software packages that they rely on just in ECP, and each of those has its own dependencies. There's something like 5 plus target architectures that we have to think about. Maybe not Xeon as much anymore, but Xeon, maybe not KNL as much anymore. But there are plenty of different platforms, including laptops, because people do a lot of their development on laptops. 7-ish compilers across the different systems, 10 programming models, if you include everything that's in ECP. And then 2 or 3 versions of each of those because some version of one of them is subtly different and incompatible with some version of another one. So if you multiply that all out, that's like 1.2 million combinations of software that we might care about. And that's not sustainable. It's not feasible to build all of that stuff or to make sure that it all works. But this is essentially the software ecosystem that HPC people are trying to use. And so every application has its own dependencies. Developers devote tons of time to getting this stuff working on custom HPC platforms. And you often trade usability for performance. So if you get the thing working and it works for your customers, even if it's not getting the most out of your machine, you might keep it there just because it might take you another 2 weeks to build the whole thing. And so we need something easier to actually rely on other software in this domain. And so just to emphasize this point, in around 2013 when I started this project, this was how I built stuff on my Mac. I would just say port install LiveElf. It would go and say, okay, I built LiveElf. Done, you have LiveElf. That's great. All I had to do was name the package. If I want to install something on a supercomputer, well, I download all 16 tarballs that I need. I go and start building, and then it looks like this. And I fight with CMake and AutoTools and something else install and so on. And then I go and run the code, and it segfaults. And I start over and build it all again. So that's not workable. So people often ask me, what about modules? What don't modules solve this problem? And they don't, because modules are really only, they're only telling you how to set the environment for something that's already installed. And I think a lot of cluster users don't realize this, that there's actually, in general, at HPC sites, there's a team of people, or one very tired person who went and installed all the things that sit underneath your modules. And the fact that you can just type module load GCC at some version, well, someone had to build that, and someone had to make sure it was installed and to make sure it worked. And that was all manual. So the other question I get often is, what about containers? Well, containers are awesome. They're a great way to reproduce and distribute a software stack. You can bundle your application with all the dependencies that you need, but someone still needs to build the containers. And so you still have this problem if you're distributing software in containers. It's just that it's much easier to reproduce. The difference is that your users now don't have this problem because they can just run the container, but you still have the problem, and the developers who work with you on your project still have the problem. So we need something more flexible to build containers. And yes, inside of a container, there's generally an OS userland package manager. That's true. But those things are built to build basically single versions of software, or to build the version that the OS maintainers deemed stable. They're not giving you the bleeding edge version of things that you need for your development, and you don't have a lot of flexibility around that. So you need something else. So Spack is a package manager for HPC designed to address this problem. If you want to use Spack, all you have to do is go to GitHub, clone Spack, source an environment script, and that's optional, and then just run Spack install piece of software. And the idea is that when you say that, if you say you want to install HDF5, Spack will go and say, okay, I know all the things that HDF5 depends on. I'll fetch them all, I'll build them all, and I'll get them installed for you so that you can go about your day and focus on the science that you're trying to do. It is sort of like other package managers in that you just name the software that you want to install to get it on your system. It's not like other package managers in that we try to make it very flexible so that you can install exactly what you want instead of just what the distro provides. So if you look at Spack from a user interface point of view, here's what you might see. If you say Spack install, say MPI leaks, which is a tool that we developed at Livermore for debugging MPI programs, that's unconstrained. It says, I just want MPI leaks, just get me MPI leaks, however it makes sense, and get that installed for me. And Spack will go and fill in the details that you need to get that installed. If you want to be more specific, if you're not happy with the defaults or if you want a particular version, you can actually say that. You can say, hey, I want to install MPI leaks at version 3.3. You can be even more specific. You can say what compiler you want, what compiler version, and we will swap that into the build and build the thing with that compiler instead. You can have options. If the package maintainer provided options on the package for different configure options or other things that may be different with different builds of the package, you can specify that too. So you can say plus threads, minus threads. You can have parameterized options that take string values or lists. And then you can also inject flags in your build. So if you need to build an entire stack with a particular set of flags, you can do that from the command line. You can say, I want to build MPI leaks and all of its dependencies with these particular C flags, and I want that to propagate through the entire DAG of dependencies. You can be specific about the target that you want, at least on some platforms right now. So on the Cray, we let you set the target to something very specific, like a Haswell or a Xeon Phi for the back end. And then finally, that syntax is recursive in the sense that if you know that you want to build MPI leaks, not with just the default MPI or not with just any MPI, but specifically one version of MPI, you can say that. You can say, I want to build it with this particular version of a dependency, and all the same constraints can apply to your dependencies too. And so the idea is we've built a language that you can use to describe what it is that you want to the package manager, or at least the parts that you care about. And Spack will go and try to get you a build of that based on the recipes that it has on file. Also from a user perspective, if you want to know what's available in Spack, it has the basic commands that you would expect from a package manager. So if you say Spec List, it tells you what's available. There's about 3,000 packages in Spack now, so there's quite a few things that you can probably leverage. Note that on this screen, those are just package names. They're not specific versions or anything. Those are all templates. Those are the things that you can try to build. And then if you want to see what you've actually installed, there's another view. So if you type Spec Find, then what you'll see is the exact versions and the configurations, the compilers that things were built with. And so one thing you'll note here is that, so up here, there's 2 identical versions of dynenst, and I think there's 2 identical versions of adept utils there. They're not exactly identical. They're actually different configurations. And so the other thing that Spack does is it stores all the metadata for these things, and it allows them to coexist on a single cluster so that you can have all the different versions that you want. You can experiment with different ways to build things to see if you get more performance or to fix bugs. And Spack will remember the configuration. And so if you really want to drill down on stuff like that, then you can provide a little more syntax to Spec Find. You could say, Spec Find me all the versions of call path. And if you want to see the dependencies, you can provide options to really drill down into the metadata there. So like for example, these 2 seemingly identical versions of call path are actually built with 2 different compilers. This one's with Clang, this one's with GCC. And then if you drill down further than that, you can see that actually they have different boost versions that they depend on. And so if you're wondering, for example, why you can't build against this library or why your C++ compiler is exploding, you may be able to find pretty easily what the ABI problem is there. because we actually retain the information about the versions that things were built with. So beyond that, Spack makes it easy to install, to write your own package recipes. So if you want to write one of these recipes, if you want to make it possible to build something in Spack, suppose that you want other people to use your software, or you just want to experiment with different ways to build a piece of software, you can make a simple Python class like this. We have some boilerplate commands that'll just generate sample versions of things from a tarball. And essentially everything is a Python class. And we have a DSL in Python at the class level for basically telling Spack all the metadata associated with the package. So you can see here that there are different versions that this package can be built with. It has checksums so that it knows how to download those different versions of the package, and it can guarantee you that you're getting what the packager intended. There are dependencies down here. They can be different types. You can have build dependencies, link dependencies. And you can also express constraints on your dependencies with the same syntax I showed earlier. So like with boost, you can say, this package depends on boost 142 or higher, or things like that. And it's the same syntax that you would use on the command line to say, I want a specific type of Spack install that you use to express constraints inside the package. And then the build recipe itself is this install method. This should look pretty familiar to people who have built things before. It's just calling cmake with some arguments, but they're templated. So you can say, okay, Spack has told me how I should build this thing. It already installed all my dependencies for me. We give you objects that tell you where those things are installed, and then you can just pass those to your cmake line or your configure line. Yeah?
Yeah, one of the things with this is that in Linux, you've got 3 different places where you can install stuff, right?
Yes.
There's no real, generalized schema for where to put it. And so if you're just taking stuff from me, and nobody's like defining, I mean, like most people, when you can compile all this and install it, it all works, but then you've got simple resolution errors all over the place. So did you guys have any, like, kind of like a schema or any kind of a standardized abstracted file system?
We do.
Kind of like namespaces and directories. So if you have a particular piece of software that you have versions of it,
Yes.
a lot of times, at least when the nightmare we had was everything would be installed inside of like a bin directory. You have 3 different versions. There's collisions.
Right.
I'll install it. It's dumping it in the same freaking one monster directory.
So we do have that one monster directory, but it's organized. And so this is the monster directory that Spack has. It's actually my next slide, so that's a great segue. If you think of each piece of software as a graph, like the ones that I showed earlier, the way that we version things in Spack is that we take that entire graph and imagine that those nodes aren't just names, but they also have like the version, the compiler, the other attributes of how the thing was built. We take that whole DAG for everything that we install and we hash it. And then that gets you this directory layout down here. So really, if you just wanted to guarantee uniqueness, all you would need would be the hash for each of the directories. But we provide a little bit of information so that you could navigate this if you decided to.
So everybody that compiles to the Spack system has to abide by that schema.
To some extent, and I'll talk a little bit about that later, but basically this is the install layout. You can create views of that, and so if you want your users to be able to navigate some other directory hierarchy for this, we have ways of specifying that. So,
Does that mean that everybody had to then build recipes for all the different software, including potential commercial software in Spack?
yes, yeah. And so if you do that, then you have a template and you can go and generate 100 versions of your favorite thing. So the other thing that we do here to ensure that each of the dependencies will run correctly is that we embed RPaths in the binaries. So who's familiar with RPath? Do people know what that is? Yeah, so not many. Who's familiar with LD library path? More. So essentially, when you install libraries like this, you need a way for the dependent package to find its dependencies. And so the Linux linker uses environment variables or configuration in the etc directory usually for system distributions. But in Spack, because we're installing so many things, we embed RPaths in the binaries. So every binary knows how to find its dependencies. It knows where they are. So they can all coexist in this directory. And when you run the thing, our opinion is that you knew what you were doing at build time, or at least the package manager did, and it should know where the dependencies live, and it should just put that in the binary so that when it gets to be runtime, you don't have to remember all that, because the person who runs the code may not even be the person who built it. So it doesn't make sense for them to have to know the locations of 50 dependency packages in order to just get the thing running. So we don't require modules. We will generate modules for you for all these things so that you can load them on demand. but you don't have to use them. They will just run if you just run the binary from Spack.
Sorry, just one other
Okay.
Do anything where you run like a certain test to make sure that once you've installed it, right, you're not going to get a runtime error, so you know that this actually works.
So we do on our clusters, but it's not integrated into Spack yet. We don't have testing there at the moment to embed in the packages. It's something we'd like to put in. Cool. A couple other things about the dependency model. Just as the packages are templates, they don't depend on specific versions of their dependencies. We also allow you to depend on specific versions of interfaces. And so we have these things called virtual dependencies in Spack, and it's particularly important for HPC because there's a lot of libraries like BLAS, LAPACK, MPI that aren't really libraries, they're interfaces. And there are lots of implementations of them, and they may have different library locations, different headers that you have to include for different versions of them. We abstract that by making the packages in Spack depend on the interface. So you say, I depend on MPI, or I depend on MPI2 in your package. And then if the user wants to install that package, they can say what MPI they want it to build with, but we'll check to make sure that it's implementing the right version of the interface. And so you can make very generic packages and basically build the same thing with different compilers, different MPIs, different BLAS implementations, and so on. And the way this works is, when you say Spack install, say MPI leaks with the call path at version 1.0 plus the debug option and this specific version of the LiveElf library, we go and we resolve the dependencies for you. So we concretize that abstract specification. And basically what that means is that we build out the DAG, we put all the constraints that you asked for on it, and then we go and solve for what possible ways we can fill out all the blanks, basically. And it turns out this is an NPHard problem, solving for constraints like this. Because if you have packages laid out like this, and say you have A, it depends on B and C, they depend on different versions of a dependency, you can get a conflict. And so basically you have to search that configuration space to find a version that satisfies the constraints that the user asked for. But Spack's doing this work for you. It's not quite doing the whole NPHard sat solve yet. We're adding that right now, but it does a pretty good job with the heuristic algorithm that it has. So since we created this in 2013, Spack's gotten a lot of usage worldwide. This is the users from different locations who have accessed our documentation site. We think that's a pretty good metric of how many people are using Spack. We have over 1,100 monthly active users on the doc site alone. And we've been downloaded 150,000 times in the past year. So we're trying to catch DK's download counts, but we're not quite there yet. And so we have over 350 contributors from labs, academia, and industry who have added lots of different things to Spack. Some of them have contributed entire features. We've gotten LMOD support from people, support for different module systems, lots of core stuff. And then some people just add new versions to packages as they come out because it's pretty easy. And so the only reason that we're able to function is because we have a community of people who help us out with updating these things. Just to give you an idea of how active it is, we merged something like 232 pull requests in the month leading up to our release at Supercomputing this past year. So it's a pretty active community, and it's not just one person. Although like for this month I was the top contributor. That's not actually usually the case anymore. And there's a whole lot of people who are doing commits to Spack, and not just the core team at Livermore. This is a graph of how we've benefited from external contributions. The top plot is basically showing the lines of code in the packages, so the actual recipes in Spack. And you can see that there's a lot of organizations that are contributing there. This green line is Livermore. So basically, up until our paper at SC15, it was pretty much just a Livermore project. And then after that, Livermore continued to grow in terms of the number of contributions we were making in the packages. But the community support was overwhelming. We wouldn't have nearly as many packages now without these external contributions. And then down here in the core, this top part is Livermore. So we're still making a very significant number of contributions in the core and trying to manage the community. But we have significant contributions from other places. So this is EPFL. We have a collaborator there in Switzerland who's helped us out a lot. And also the folks at Fermilab and CERN have added some really cool features to Spack. It's used on many of the top HPC systems. So right now, I think I looked at the top 500. We're used on at least 6 out of 10 of the top 10 to deploy software, which is pretty cool. We're used in other countries, as you saw from the plot before. And the other interesting thing is that Spack has become pretty popular in other communities. So the high energy physics community, They don't do HPC the same way that we do, but they've adopted Spack because they think it matches their development workflow. And so they're working on a lot of features to help developers keep updates flowing to their software. We just released version 0.12. I'll talk about the big feature in this release, which was environments. But the other major piece of news there was we were originally an LGPL project, but we actually went through and relicensed all of Spack to be Apache 2 or MIT, which was painstaking because we had to get approval from all of our 350 contributors. But we really wanted to be friendly to industry, and so we wanted to move to a more permissive license from the LGPL license we were originally under. And we figured the earlier we could do it, the better. So it's done. Spack environments are one of the new features that we've introduced. You saw the Spack install syntax. You can say Spack install package with constraints. It's great for installing sort of one-off pieces of software, and you can script that. But we wanted to make it easier to install lots of software at once. And if people have used package managers from languages like Rust or say Ruby or or JavaScript even, it's much nicer to work with software in those languages. You can make a file that says, here's all the things I want to install, and you can just say install. And a lot of projects will come with files that just describe their dependencies. And so we wanted something like that for Spack, so we've implemented this Spack.yaml format that defines the environment that a piece of software could run in. And so basically what you do is you can include some configuration, you can do all sorts of different types of Spack configuration in there that's specific to your project, and you can also list the packages that your software depends on or that you want in an environment. And then if you have one of these in a directory, you can just cd in there, type Spack install, and it will install all the things that you asked for. It'll spit out a lock file, it's not a Unix lock file. It says, these are all the versions and configurations of the things that I installed. So it's sort of a lock on the configuration. And if you want to reproduce the environment, you can hand that to someone and say, here, rebuild exactly what I built. And they have a precise description of it. The other cool thing about environments that I think this has a lot of potential is that they can help with building containers. And so if you think about packaging an application up in a container, then you probably want to install that application. You may want to install some other workflow tools to use with it or something like that in your container environment. And so right now, if you want to do that, you would have to write a Docker file. You may have a whole bunch of scripting in there. You probably have to script your entire build manually to get things installed in the container. So with Spack environments, you can basically put a Docker file in a repo alongside a Spack.yaml file. And your Docker file could look like this, where you say, OK, from Spack CentOS 7, we're providing images on Docker Hub now with Spack pre-installed in different OSs. You could say, here's my working directory, copy the Spack.yaml in, and just say Spack install. And it'll go look in your Spack.yaml and install all the things that you asked for you. And you can figure out what you want to do with those in your container. And then in your Spack.yaml, you just put the things that you want to install. So if you want to match the container to a particular machine, or you want OpenMPI built a certain way because it matches your system MPI, you can do that. And then once you're done with that, you can kick this whole thing off with Docker build, and you could run with Singularity or some other container solution. So that's what's in Spack right now. I want to talk a little bit about the roadmap, just where we're going. There are a lot of features coming up. We're going to be supporting ECP. Spack's the official software distribution tool for ECP. And the packages, like the software packages I talked about in the beginning, are actually going to be distributed using Spack. Spack Stacks is something that we're doing for facilities. I'll talk a little bit about that. And we have a couple of other features that I'll talk about in more detail coming up. So on ECP, when you have 80 software packages and 15 applications that you want to work together, you really need some way to bundle up builds and to have developers be able to hand things off to each other. And so under ECP, we're using Spack to manage developer workflows. We're using it to basically do periodic releases of groups of related software that they're calling SDKs. And I think XSDK is the example that's probably most known. It includes most of the major math libraries. That's really helped for basically getting these HPC developers who previously didn't try testing their software with other packages to make sure that it worked together. They've been able to basically use Spack as a harness and much more frequently test integration with other math libraries. And so that's been helpful. We're working on continuous integration solutions under ECP so that we can more frequently test Spack packages, test developer software. And so we actually have a contract under ECP that I'm also involved in managing along with Rob Neely. We're working with a vendor called Onyx Point to add some features to GitLab so that we can run GitLab CI in HPC centers securely. I think continuous integration has long been something it's been hard to run on-prem, especially in the way that HPC clusters work, where you have to run as your user. And so what we're adding here is support so that a GitLab runner can set UID to the user that you were in GitLab when it's on the cluster. And that fits our security model at Livermore and at a lot of other HPC sites. And there's also a batch runner that knows about Slurm, LSF, and Cobalt, so that we can use the HPC cluster as a CI system if we want to. We can have a partition that's dedicated to CI and run as users on the cluster. So we want to leverage that in Spack, and so we are actually building infrastructure so that Spack can have binary packages too. And so what we want is, right now, if you're a user and you submit to Spack, you send a pull request to GitHub. We run a small set of unit tests on that, and that's it. We're really just testing the core of Spack. We do some build tests, but we don't have the resources right now, or at least the automation, to do more extensive testing. And so we're adding the ability to take the source archives that people provide. So these are basically the tarballs with the source, upload them to a mirror in Amazon so that they would be available later, say if the original site went down, and then people could download those. And we're also using GitLab CI to go do builds in the cloud. So we're building in EC2 under Amazon right now to produce binary packages that we would also put out on the internet for very specific versions of things that are optimized for different architectures. And so the idea there is that then users could download the binary package. They wouldn't even have to build. And we could potentially loop HPC centers into this as well. And so if you log into a capability machine in the DOE, hopefully one day, you'll be able to say Spack install package. You won't even have to build it. There will be an optimized binary for that platform available that's reusable, and you can just run. So the other feature that's on the roadmap is Spack Stacks. So we're trying to automate entire facility deployments, not just user deployments or container deployments, but we want to automate everything that facilities do to deploy software in a single YAML file, kind of the same way that we did with environments. And so the idea here is that it's a YAML file. It's a little more complicated. You can provide some definitions of lists of specs. These are the same specs that I described earlier, but they can be things like the compilers that I want to build with. They can be the MPIs that I want to build with. And then I could have a list of packages like this. And so a facility could basically map out the different tool chains they care about, the different MPI implementations they care about, and the list of packages that they care about installing. And down here in the specs section, just like with the Spack.yaml, we have this matrix thing that takes the cross product of all that stuff and just tells Spack to go and build it all. And that could install from binaries, or it could build from source right on the system. You can also include things like module configuration, or, and I'm not showing it here, but you can generate a view of this that basically has some site-specific directory layout so that if users want to browse this in the file system, they can, if they don't want to just access these things through modules. So this is sort of this is a combinatorial version of an environment. It's basically automating the facility deploy. And then the final new thing that we're trying to do is we're trying to introduce specific target information in our specs. So if you think about what I just showed, where we're trying to set up a build farm for Spack, one of the very important things about that is that you really need to know enough information about your binary so that you can reuse it on the system, so that you know that it's ABI compatible with the other stuff that you want to install. And you also want to know how it's optimized, or what architecture or what ISA it supports. So we're trying to add very specific architecture information to the specs so that you can know not just that something's an x86-64 binary, but that it's a Skylake binary, and that it supports AVX 512 or something like that, so that when you pull down the binary package, Spack would say, hey, I see that there's all these binaries available. This one's built for the closest architecture to the one I have with the most features. I'm going to use that one instead of the generic x86 one that doesn't use half my CPU. So that's the goal. And this is on the roadmap. We're going to try to get this in this year, along with better dependency resolution, so that we can actually go out and pick which binaries may work best on a machine. And so there's just generally a lot of stuff going on in the Spack community right now. It's growing rapidly. It simplifies HPC software development, not just for facilities, but also for developers and users. And it gives you a lot more flexibility, I think, than other solutions. So more than your OS package manager, because you can build stuff from source when you need to. We're trying to work binary support in with all this flexibility, which is a hard problem. And this is being used in ECP, which is pretty cool. And so, like I said, we have a lot of roadmap features. So check out Spack. Go to GitHub, give us a star on GitHub, download it, try it out, and see if you like it. And there's lots of resources if you need help. There's a mailing list. There's a Slack site. And we can just file an issue on GitHub. So thanks. questions? Yes.
Are you planning or you already have established certified programs for engineers that you can certify them using Spack and maintaining Spack?
We don't have a certification program yet, but that's a good idea. I guess, we have tutorials at supercomputing. We're trying to get one into ISC for this year. We try to give tutorials. You can actually go online to our documentation site, and all of our tutorial material is online. So if you want to take the same tutorial that we do at SC, that's available online with all of our materials.
I guess it's just missing the blessing for you to tell the
Yeah.
industry, this guy knows how to do it. You will be certified. Now, I'm sure you know ECPO.
Yes.
Do you consider them a sub-competitor or a par? Or
They're probably our main competitor.
yes?
So,
a
yeah.
par, or
Sorry, so could you say that again?
how do you position ECPO from you?
I would say they're both trying to solve the HPC packaging problem, but in different ways. So I would say Spack is a package manager, and it it actually does dependency resolution like I showed. If you say I want to install this package, it'll go and figure out what versions are needed for the thing you asked for. EasyBuild is very specific, and so they'll do phased releases, and they have configurations for specific versions of things. And you can make your own configurations and expand that, but they're very much, I would say they're not as flexible as this in terms of what you could get working on a capability machine. So they have a really good release pipeline, but yeah, they're not a package manager.
I would find in Spack a release pipeline too.
So that's the build pipeline that I showed that we're building for ECP. And so we're working on actually having binaries available for our releases. And so that's another thing EasyBuild does not do. They don't do binary installs at all. So there's a lot of features that we have that they don't. And then there's this versioning philosophy that's very different between the two systems.
And if I were to have binary releases, then the users of my code will actually won't have access to the code at all. They will only be able to use it and get the results, but they will never know the secret of my software.
That is possible, because you could just make binaries. But you could also provide them with a recipe so that they could generate different versions of it, if you want to, right? So if you want something proprietary, you could do that because we have binaries. Or if you do build from source, then you could both have binaries for versions that you've vetted, but also allow them to build new versions in case, like you were saying, you want a new version at your site because the packaged version doesn't work. You want to rebuild some aspect of what's available.
Thank you.
Yeah. Yep. Could you say that one more time?
Can you work with Bazel?
We're trying very, very hard to work with Bazel. It is not easy because they try very hard to make themselves unpackageable. And so what I mean by that is that like the TensorFlow build, for example, vendors all of the dependencies into the build. So we're working on splitting that out so that we could actually make a templated TensorFlow build, but we don't have that in yet. But on the other hand, Bazel is in Spack. You can install it, and I think we could work with Bazel.
I guess you can generate Bazel configuration style.
Yeah, we could. You can essentially do anything in the build. I think Bazel is just particularly hard to work with. And so we haven't devoted the resources that it would take to just maintain a Bazel package the way that we would like. Yep.
This works transparently whether you're in a conventional Linux environment and an HPC environment?
It works fairly transparently, except I would say on the HPC environment, one of the things that you really want to do is set Spack up so that it knows about like your system MPI. So if you get a vendor-optimized MPI or vendor-optimized other packages like the math libraries, we have ways that you can say, here's where the MVAP pitch that came, or the vendor M pitch that came with the system lives. Here's where the vendor MKL implementation lives, and so on. And so you can basically tell your packages to build with those external dependencies. And so I think that's the main difference. If you set this up on your laptop or on your own cluster, you might just build your own MPI. But if you're using a solution from some vendor, you really want to use the optimized versions that they ship to you. And so we have ways to do that. And so it's configuration difference. Yep.
First of all, I applaud you for taking this on, if you just asked.
Thanks.
Big headache for some developers. My question was around the workload managers or schedulers.
Right.
How are you compatible with Slurm and Altair's?
So the way that currently works is its configuration. So the packages like MPI will have options on them that say what scheduler fabric what scheduler you're building with, what fabric you're building with, things like that for the host system. And so yeah, we're compatible in that we'll build a version of MPI that will work with those. But you do have to do some configuration to get those types of installations installed.
And I would also think that with like Bright's cluster manager, you operate that, it doesn't really matter.
I don't personally have experience operating with Bright. I would like to think that someone out there does or has used Spack on a Bright cluster, but I haven't myself. So yeah.
Thanks.
Sure. Other questions? Yes.
Can we have you back?
Sure.
Tutorial?
Sure. Yeah, for sure.
Thank you very much.
All right. Thanks a lot.